This video is related to multiple choice questions of topic coordination chemistry. This is part second of coordination chemistry. You can also see first part on my Swapnali S Jadhav channel. Like and share my videos to your friends also. Let us start the questions. First question: complexes having same chemical composition but exhibit different physical and chemical properties called polymers, isomers, chiral, asymmetric. So complexes having same chemical composition, that is same empirical formula but exhibit different physical and chemical properties are known as the isomers, that is option B. Then next, isomers can be broadly classified into options are stereoisomers, structural isomers, both A and B, and D option coordination position. So isomers can be broadly classified into stereoisomers and structural isomers. Means correct option is option C, that is both A and B. Isomers differ in bond connectivities are called stereoisomers, structural isomers, optical isomers, none of these. So isomers differ in bond connectivities are known as the structural isomers, option B. Isomers having same structural formula but different relative arrangement of atoms of ligands in space are called stereoisomers, structural isomers, both A and B, none of these. So such type of isomers, that is having same structural formula but different relative arrangement of atoms of ligands in space are known as the stereoisomers, option A. Which of the following is subtype of structural isomers? Optical, geometrical, cis-trans, coordination positions. So structural isomers having subtypes. Which are the subtypes? That is ionization isomers, hydrate isomers, linkage isomers, coordination isomers, and coordination position isomers. Means from option, which one is correct? That is option D, coordination position isomers is a subtype of structural isomers. Which of the following subtype of stereoisomers? Options are ionization, geometrical, linkage, hydrate. You know that ionization, linkage, hydrate, these are the subtype of structural isomers. So correct option is B, that is geometrical isomer is subtype of stereoisomers. Also stereoisomers type is optical isomer. Optical and geometrical are subtypes of the stereoisomers. Coordination compounds with the same chemical formula but differing only in their relative positions in space occupied by their constituent ligands or atoms is called isomers. Geometrical, structural isomers, optical isomers, none of these. So coordination compound with the same chemical formula but differing only in the relative position in space occupied by their constituent ligands or atoms are known as the geometrical isomers. So geometrical isomers further divided in two types, that is cis isomer and trans isomer. We see in next question. In isomers, adjacent positions are occupied by identical ligands, cis, trans, hydrate, none of these. So in cis isomers, adjacent positions are occupied by identical ligands. In trans isomers, positions are occupied by identical ligand. So in trans isomers, opposite positions are occupied by identical ligands. If the plane of polarized light is rotated to right, it is called form. Dextro, leo, racemic, none of these. So if the plane of polarized light is rotated to right, it is called the dextro form. While if the plane of polarized light is rotated to left, then it is called the leo form, option B. Equimolar mixture of two dextro and leo isomers is called dextro-rotatory, leo-rotatory, racemic mixture, none of these. So equimolar mixture of two dextro and leo isomers are known as the racemic mixture, option C. Optically active complex must be dot dot. Chiral asymmetric, their mirror images are not superimposable on each other. All of these. So correct option is option D. Optical active complex must be chiral, must be asymmetric, must be their mirror images are not superimposable on each other. Then next, optical isomer must be dot dot, solid, symmetric, gaseous, asymmetric. So correct option is which? That is asymmetric. Trans dichlorobisethylene diamine cobalt third is optically inactive because dot dot, it contains a plane of symmetry, it does not contain plane of symmetry, it does not contain axis of rotation, it does not contain mirror plane. So correct option is option A, it contains a plane of symmetry, hence it is optically inactive. When coordination number 4, possible structures will be dot dot, octahedral, tetrahedral, square planar, both B and C. So when coordination number 4, then structure will be tetrahedral or square planar, means correct option is D, that is both B or C, tetrahedral or square planar. Geometrical isomers are not possible in dot dot complexes, octahedral, tetrahedral, square planar, both B and C. So geometrical isomers are not possible in tetrahedral complexes. When coordination number 6, possible arrangements of the ligands around central metal atom or ion is or are dot dot, octahedral, planar, hexagonal, trigonal, prismatic, all of these. So when coordination number 6, then possible arrangement of the ligands around central metal atom or ion is octahedral or planar, hexagonal or trigonal, prismatic, means correct option is D, that is all of these. Which of the following type of tetrahedral complexes show optical isomers? Ma4, Ma3b, MABCD, all of these. So only MABCD type of the tetrahedral complexes shows the optical isomers, means correct option is option C. Which of the following type of octahedral complexes shows facial or meridional isomers? Ma4b2, Ma3b3, Ma2b2c2, all of these. So facial or meridional isomers are shown by the Ma3b3 type of the octahedral complexes. Which of the following isomers have the position of ions are within or outside the coordination sphere? Coordination isomers, linkage isomers, hydrate isomers, ionization isomers. So ionization isomers having the position of ion are within or outside the coordination sphere. For example, here complex CONH3 Br SO4 and CONH3 SO4 Br. In first compound complex, Br minus is within and SO4 minus minus are outside, while in second SO4 minus minus are within and Br minus are the outside. Okay, then this is the example of the ionization isomers. The next, in hydrate isomers dot dot are replaced by water molecules, cations, anions, complex ions, ligands. So in hydrate isomers, ligands are replaced by water molecules. So for example, in complex Cr H2O4 Cl2, here one water molecule is replaced, H2O5, here becomes H2O5 Cl2. So here chloride is replaced by the water molecule, hence this is example of the hydrate isomers. Next, in coordination isomers dot dot are interchanged between cationic and anionic parts of the complex, metal atom or ions, ligands both A and B, negative ions. So in coordination isomers, metal atom or ion and ligands are interchanged between cationic and anionic parts of the complex. For example, Cu NH3 4 PTCl4, and here in case instead of copper, platinum NH3 4, and here CuCl4. That is both cationic and anionic parts of the complex are interchanged, hence it is example of coordination isomers. Then next, a ligand having more than one donor atoms but links through only one atom at a time is called dot dot, unidentate, polydentate, flexidentate, ambidentate. So such type of ligand is known as the ambidentate. For example, SCN minus, NO2 minus, etc. When NO2 is linked through, SCN may be linked through sulfur or linked through nitrogen, NO2 linked through nitrogen or maybe oxygen. Okay, remember that, hence it is known as the ambidentate ligand. Linkage isomers contain dot dot ligands, unidentate, polydentate, flexidentate, ambidentate. So linkage isomers contain ambidentate ligand. Okay, then next, coordination position isomers are related to dot dot complexes, cationic, anionic, neutral, bridged. So coordination position isomers are related to bridged complexes. We see one example of that, that is NH3 4 CO NH2 O2 CO NH3 twice Cl2. Okay, and here Cl, one Cl is replaced here, one NH3 here, Cl NH3 thrice CO NH2 O2 CO, here becomes NH3 thrice Cl. Okay, so this is the example of the coordination position isomers, remember that. Next, VBT, that is valence bond theory, was successfully applied to complexes by dot dot Alfred Werner, Lewis, Linus Pauling, Sidgwick. So correct option is option C. The hybridization in inner orbital octahedral complexes is dot dot sp3 dsp2 sp3 d2 d2 sp3. So the hybridization in inner orbital octahedral complexes is d2 sp3, option D. sp3 is for tetrahedral complexes, dsp2 is for square planar complexes, and sp3d2 is for outer orbital octahedral complexes, remember that. The complexes containing unpaired electron or electrons are dot dot paramagnetic, diamagnetic, both A and B, none of these. So when in complex unpaired one electron or more than one electrons are present, then it is known as the paramagnetic. The complexes containing paired electrons are known as the diamagnetic, remember that. CuCl4 2 minus ion is dot dot paramagnetic, diamagnetic, ferromagnetic, non-magnetic. So how it is determined that CuCl4 2 minus ion is paramagnetic or diamagnetic? So in CuCl4 central metal atom is copper. Okay, but copper is in which oxidation state? In 2 plus. Cu is in 2 plus. We know outermost electronic configuration of copper is what? 3d, for understanding we 3d9 4s2. Okay, so 2 electrons are removed from 4s2 and copper contain which electronic state configuration? 3d9. Okay, so we put the electron in orbital 3d9, 1 2 3 4 5 6 7 8 9. Okay, and this 4s and 1 4s and 3 4p orbitals are available for hybridization, it undergoes sp3 hybridization. sp3 hybridization means geometry is tetrahedral. Okay, it contains one unpaired electron. How many unpaired electron? One unpaired electron, therefore it is paramagnetic. Okay, so we see question now. CuCl4 2 minus ion is dot dot, so it is paramagnetic. Why paramagnetic? Because it contains one unpaired electron. CuCl4 2 minus ion is dot dot, square, planar, tetrahedral, octahedral, none of this, so it is tetrahedral, option B. NiCl4 2 minus ion is paramagnetic, diamagnetic, ferromagnetic, non-magnetic. So we see that NiCl4 2 minus, here nickel is also in which oxidation state? Ni 2 plus, therefore outermost electronic configuration is 3d8. So 1 2 3 4 5 6 7 8. So here chlorine, this is ground state electronic configuration. Chlorine is weak fielded ligand, hence pairing is not occur, so it remain as it is 1 2 3 4 5 6 7 8. Therefore outermost sp3 4s and 3p orbitals are available for hybridization. Okay, hence hybridization is sp3, that is it shows tetrahedral geometry, and here presence of two unpaired electron. You may also ask how many unpaired electrons are present in NiCl4. Then remember that two unpaired electrons are present in NiCl4 2 minus ions, hence it is paramagnetic. Okay, NiCl4 2 minus ion is tetrahedral. Okay, then next CuCN4 2 minus ion is dot dot, paramagnetic, diamagnetic, both A and B, none of these. So here in CuCN4 2 minus, copper is in which oxidation state? That is 2 plus. We know that outermost electronic configuration is 3d9. 1 2 3 4 5 6 7 8 9. But here cyanide Cn is strong electron pair donor, so during formation of complex, what happen? It may forces to promote electron from 3d to 4p orbital, 3d to 4p orbital, and undergoes dsp2 hybridization. Okay, so here 1 2 3 4 5 6 7 8, and what happened? This electron is forces to 4p orbital, and therefore it undergoes which hybridization? dsp2. Why? Because this cyanide is strong electron, remember that. So how many unpaired electron present? That is one unpaired electron present, therefore it is paramagnetic. Hybridization is dsp2, therefore geometry is square planar. Hence CuCN4 2 minus ion is what? That is paramagnetic, and its geometry is square planar, option B. NiCN4 2 minus ion is same, we check. So nickel is in which oxidation state? 2 plus, outermost electronic configuration 3d8, therefore 1 2 3 4 5 6 7 8. Here cyanide is strong electron pair donor, so during formation of complex, what happen? It pairing take place, electrons pairing take place. How it is? It is in ground state, while in excited state, what happen? 1 2 3 4 5 6, and this electron here get paired, that is as it is, and it undergoes dsp2 hybridization, dsp2 hybridization. Hence here unpaired electrons are absent, all electrons are paired, hence it is diamagnetic. Okay, means answer of our question is it is diamagnetic, option B. And geometry square planar. How many unpaired electrons are present in NiCN4 2 minus? that is 0. Remember that. Then next, when dot dot orbitals are used for sp3d2 hybridization called outer orbital or high spin or spin free complex. Options are nd, n-1d, both a and b, none of these. So when which orbitals, that is nd orbitals, are used for sp3d2 hybridization, then it is called outer orbital complex, or it is also known as high spin complex, or it is also known as spin free complex. Remember that. And when n-1d orbitals are used for d2 sp3 hybridization called, sorry, here not outer, here inner orbital or low spin or spin paired complexes. Okay, typing mistake. So remember that n-1d orbital. Then next, Linus Pauling referred inner orbital complexes as dot dot complexes, hypoligated, hyperligated, both a and b, none of these. So Linus Pauling referred hypoligated complexes as inner orbital complexes, while hyperligated complexes are known as the outer orbital complexes. Okay. Then next, inner orbital complexes are formed by dot dot ligands, strong, weak, both a and b, none of these. So inner orbital complexes are formed by strong ligands, while outer orbital complexes are formed by weak ligands. As F minus is weak ligand, Fe F6 3 minus is dot dot complex, high spin, low spin, no spin, none of these. So we see Fe F6 3 minus. So here Fe, that is iron in 3 plus oxidation state, having electronic configuration 3d 5u, 1 2 3 4 5u. But fluorine is weak filled ligand, therefore no pairing. Therefore for 6 ligands, outermost 6 orbitals are available for hybridization. Hence hybridization is sp3d2. sp3d2 means geometry is octahedral. How many unpaired electrons are present? That is 5u. And here this is high spin, yellow spin, 5u unpaired electrons are present, means it is high spin. Okay, this is outer orbital complex or inner orbital complex. So this is outer orbital complex. So we see question as fluoride ion, F minus ion is weak ligand, FeF6 3 minus is, which one is correct option? That is high spin complex. FeF6 3 minus ions has how many number of unpaired electron? That is 5 number of unpaired electrons, and it is paramagnetic diamagnetic. So it is paramagnetic as it contains 5 unpaired electrons, and geometry of that complex is octahedral. We can see similar for COF6 3 minus. So for COF6 3 minus, cobalt 3 plus. So outer electronic configuration is 3d 6. Okay, 3d6. So 1 2 3 4 5 6 in ground state. Also in excited state there is no pairing, therefore it remain as it is 1 2 3 4 5 6. Outermost 6 orbitals are available for hybridization, that is sp3d2. Here 4 unpaired electrons are present, outer orbital complex and paramagnetic. Okay, so correct option is how many number of unpaired electron? That is 4. It is paramagnetic. Then it is octahedral. Option C. So CONH363 plus ion is here CONH36 is strong filled ligand. So what happen? We know cobalt having 3 plus having outermost electronic configuration 3d6, 1 2 3 4 5 and 6. But here what happen, pairing takes place internally 1 2 3 4 5 6. Therefore inner d orbitals are available for hybridization. Therefore hybridization is d2sp3. Here number of unpaired electron are 0. Here 0 electron are present. Therefore it is diamagnetic, that is option B. Then we see next question. FeCN6 3 minus ion has dot dot number of unpaired electrons 0 1 2 3. So we see that FeCN6 here iron is in which oxidation state, that is 3 plus. So outermost electronic configuration is 3d5. So 1 2 3 4 and 5. So here what happen, in this is in ground state. In excited state what happen, in excited state 1 2 3 4 and 5. So here this undergoes d2sp3 hybridization, d2sp3 hybridization, and it contains how many unpaired electron, that is one unpaired electron. Unpaired electron, it undergoes d2sp3 hybridization. Therefore geometry is octahedral. Hence answer of that question is 50. FeCN6 3 minus ion has how many number of unpaired electron, that is 1, option B. FeCN6 3 minus is dot dot complex, high spin, low spin, no spin, none of this. So only one electron is present in FeCN6 3 minus, hence it is low spin complex. Then next, FeCN6 3 minus ion is dot dot paramagnetic, diamagnetic, ferromagnetic, non-magnetic. So one unpaired electron is present, hence it is paramagnetic, and it is geometry of FeCN6 3 minus is octahedral, that is option C. COCN6 3 minus ion has dot dot number of unpaired electron. So we check that COCN6, here cobalt is in how many oxidation state, that is 3 plus. Outermost electronic configuration is 3d6. So here in ground state 1 2 3 4 5 6. But in excited state, as Cn, that is cyanide ion, is strong field, therefore pairing takes place internally, and these orbitals are available for hybridization, that is d2sp3. So this is inner orbital complex. Hence COCN6 3 minus ion has how many unpaired electron, that is how many unpaired electrons, here all electrons are paired, therefore it contains the 0 unpaired electron. So 0 unpaired electrons means it is diamagnetic, and it is in which geometry is which, that is octahedral. Dot dot complex is tetrahedral, CuCN4 2 minus, NiCN4 2 minus, COF6 3 minus, NiCl4 2 minus. So here asked the tetrahedral geometry. So this option is cancelled because here COF6, F6 coordination is related for which geometry, that is octahedral. Therefore C option is cancelled. Here Cn, that is cyanide ion, is strong filled, therefore there is formation of, it undergoes dsp2 hybridization, and geometry is square planar, therefore A and B also cancel, hence correct option is D, that is NiCl4 2 minus gives the tetrahedral geometry. Next, dot dot complex is square planar, so we see that this is the octahedral. Okay, here chlorine are the weak filled ligand, hence it undergoes which oxidation, which hybridization, sp3, and sp3 hybridization is related to which geometry, that is tetrahedral. Therefore correct option is B, that is NiCN4 2 minus is square planar. Last question, CuNH3 4 2 minus ion is dot dot, square planar, tetrahedral, octahedral, none of these. So here NH3, that is ammonia, is strong filled ligand. So strong filled ligand is present means hybridization is dsp2 and it geometry of that complex is square planar. Here we completed all multiple choice questions related to topic coordination chemistry. This is part second of coordination chemistry. You can also see first part for coordination chemistry. For this purpose you visit my Swapnali S Jadhav channel. Subscribe, like and share. Please comment in comment box your opinion about this video. Thank you very much.